Good morning, everyone. I think we can start the lesson. Hopefully, the others will join after a while. Meanwhile, the audio, is it audible and can you able to see the slide? Is it fine? Audio on the slide? Yeah, that's good. At least you are okay with that. That's good. This is chapter 6. Before starting chapter 6, I would like to remind you of one thing, which is two things. About the software to be installed is the VMware, which is the virtual box, Oracle virtual box, and Ubuntu inside. That is one thing. Did you try and succeed in that installation? Anybody tried during this weekend installing Oracle, VirtualBox, and Ubuntu? Anybody? I guess I think Nora tried. Very good. That's super. It's no issues, is it, Nora? Hopefully, no problems. Okay. If you didn't try, no worries. Our class is on Thursday. On Thursday, I would like to try the command line arguments for the Linux command line arguments. So that commands we need to study at least for this week. So later on, we can pick up with the shell programming. Okay. So I'm going to start. I have some problems. So you will try to solve. Okay, sure. Is it fine, Nora? You able to finish it? No worries. Everybody, please try by following the guide. Installation guide is there. So as I mentioned in the last class, I mentioned that try to have the guide in a printout form or in another device. So follow the steps while you install in the computer. Okay. So remember the steps. At least go through the steps one by one. But remember, that guide is using the older means not very old. No. The previous version. Okay, so it's an older version of the Ubuntu and VMware. Now we have the latest version. So when you install, the steps may differ, like up and down. Some, like for example, choosing the language and the country, like we need to choose English and the place is Riyadh. You need to choose Riyadh. So that type of selection will come earlier. But in the guide, what I posted in the blackboard, the place, choosing the place and the language will come later. The steps will be given at the end because it's an older version of Ubuntu. Okay, that's it. So you will have the steps arrangement up and down. Maybe step 3 in reality, maybe step 4, something like that. Okay, but go through the steps so you will remember if the question is like this, what to choose or something like that. Okay, remember that steps. You don't have to select many things. Only the thing is you need to choose the place. You need to choose Riyadh. Language is English. I think English is by default, it's English. You don't have to choose, I think. Only the place you need to choose Riyadh. If you didn't choose Riyadh, maybe you choose whatever other places, no worries, it's not a problem. Okay. Only thing when you have Ubuntu is two main thing you need to do is the memory. By default, it will be 1024. You need to go for 2000 for at least. Bigger than that, it's okay. At least 2048. If you go for 3000, 4000, no problem. That is one thing for memory. And for storage, by default, it will be 2 GB. I think you need to go for 10 GB or 20 GB. It's written in the guide. You need to choose that memory assignment only. That is compulsory. The rest are all, it's already there. You just go click, next, something like that. Okay, then so that is the one thing. Please don't forget to choose that for the next class Thursday. Okay. How about the lockdown browser? Did anyone try to install it? Lockdown browser? Anybody? I think I made an announcement in the, not announcement, I gave you the link for the lockdown browser download in the course content. Which done tried, that's good. Just download it. Okay, you don't have to do anything, just download and install it. That's it. You will be using it for the test only, not necessary for the Blackboard virtual classes. You have to use the lockdown browser, no need. You will use that browser whenever I give you the online test. That's it. Okay. Week 4, I'm planning to have the quiz 1. If not week 5, okay, either week 4 or week 5. I need to see the schedule because we have our NCAA visit also. So I will choose and I will let you know. Okay. Most probably, I prefer week 5. That is my preference. So most probably we will fix week 5. Okay. Anyway, this is week 3, so it's time to fix it. My preference is the first class. Are you okay with that? So we can fix the date and time. So later you won't have any conflict. Is it fine with you all? Week 5, first class, quiz 1. Chapter 1, the first 2 chapters. Chapter 1, chapter 3. I can't able to, yeah. Hopefully you are okay with that. That's good. I will make an announcement, no worries. Okay. Just a second. Yes, very good. Just 1 second. So, week 5, first class, that is on Monday, we will have the quiz 1, the 2 chapters, 1 and 3. Okay, that's the portion. The type of question, as you know, that it can be true or false, it can be, I don't prefer true or false, but let's see, multiple choice questions, maybe writing a short answer, don't think it's a big answer, writing a short answer, and maybe writing one word or few words, like listing. You know that listing, it's not big answer, like what are the 2 types of this, so 1, 2, you will write only the listing, or writing like 1, 2 sentences, this type of question. Okay, true or false, I don't like it, but 1 or 2 I will include. Okay, not too many, 1 or 2 I will include it. Before week 5 test, week 4 at least, or the second class at least, we will have a practice test. We need to practice that lockdown browser. So maybe Thursday, we will try to practice. So before Thursday, you please download the things. One is the browser, lockdown browser. Another is the virtual box with Ubuntu. Okay then? No worries, I will make a announcement. Okay, all these things I will make an announcement so you won't forget it. So that's about for the next class. So we'll start this class. Before starting this class, do you have any questions or any doubts on the previous chapters 1 and 3? Mushira is asking 1 and 3. Yes, Mushira. Quiz 1, chapter 1 and 3, week 5, Monday. Okay, no worries. I will make an announcement so you will remember it. Okay, I try to do now, but it will take time. So after the class, I will make an announcement. So no worries. You will get an email notification. Okay. So I hope you don't have any questions on that 2 chapters. I can continue with this chapter, which is chapter 6. I'm going in this way, like previously we finished chapter 3, now it is chapter 6. Okay, no worries, the slide has the chapter number. So when you review, you can go along with this in your textbook. Okay, this is all about CPU scheduling. You remember in chapter 3, we studied three types of scheduler: long-term scheduler, short-term scheduler, and medium-term scheduler. So this CPU scheduling is the short-term scheduler. Okay, the one which is called frequently, short-term scheduler. Okay, so let's go to the objectives. Just a second. Actually, in this CPU scheduling, we will be looking into the scheduling algorithms. There are many different techniques available for CPU scheduling. Those are all the CPU scheduling algorithms. At least 4 algorithms we will discuss. Okay, in this lesson. And we will see, first of all, we need to know what is CPU scheduling. Then we will discuss those algorithms, how the scheduling is done, what technique we are going to use. Okay, for example, you have set of numbers, like array of numbers. I ask you to arrange the numbers in ascending order, like sorting the numbers. You have many algorithms to sort the number, is it? You have merge sort, heap sort, linear, or whatever, bubble sort, whatever, is it? So the same thing, task is to schedule the CPU to the job, a process. So how are we going to schedule? We have many techniques, okay? Before going to the techniques, let's see what is the CPU scheduling. We need to know that first. We already studied the multi-programming, concept of multi-programming in the previous chapters. It's to have many processes running in the same time. Sorry. What is multi-programming is, so we will be having more than one process running in the CPU. Okay, at the same time. So running at all times. Okay, meaning to say that CPU is not idle. That is the true concept behind this multi-program. You are not letting the CPU simply sit idle. Okay, you are going to utilize the CPU the maximum, like as much as possible. So you are going to maximize the CPU utilization. So that's the main objective or concept of multi-programming. Means if you want to achieve multi-programming, you don't want the CPU to sit idle, so you need to have a lot of process in the memory, ready in the memory, so that if CPU is executing a process, let's say P1, CPU is executing P1, all of a sudden P1 wants to read a data from the input device or a file. So it will be, the process will be moved to the device queue. It's waiting for the input device, is it? So the process will be taken out of the CPU, move on to the device queue. So now CPU is now free. In that case, you need to allot another process to this CPU. How do we allot? We need to have a list of process in main memory, so that when one process is finished or it's moved to a waiting queue, another process can be taken. You get the idea? So here you have, for example, let's see, you have a ready queue. So this is called ready. My handwriting is okay, too bad. Okay, this is a ready. This is an E, by the way. So you have a, for example, process P1, process P2, process P3, etc. So here you have the CPU. So let's say this is the processor, CPU. I write P, so it's a CPU. Okay then. Example, P1 is assigned to the processor. Sometimes P1 wants to do some task like read a data from a file or a maybe the input device. So it will be moved to the ready queue. So P1 will be moved to the ready queue. Sorry, it's not a ready queue. This is a device queue. So this is a ready queue. This one. So this one is the ready queue. Okay, and this one is the device queue. You can call it device queue or waiting queue. So let me write a waiting queue, something like that. Waiting queue means the process is waiting for the input output devices to complete. So we assign P1 to the processor. Processor starts executes P1. If P1 needs data from input and output device, it's moved to the waiting queue. So now the CPU is free. So here the CPU is free. It's not doing any task. So now the P2 is assigned to the processor. Do you get the idea? So you need a list of process waiting in the memory, the ready queue. Okay, that's the thing here. Several processes are kept in the memory at one time. At some time, many processes are kept in the memory. When a process has to wait, it means it's mentioned in the bracket, typically for the completion of some IO request. So when one process is waiting in the waiting for the IO, the operating system takes the CPU that process. So the process is moved away. It's moved out of the CPU and gives CPU to another process. So this another process is given to the CPU. P2 is given to the CPU. So this pattern continues. Every time one process has to wait, another process take over the CPU. You get the idea? This is the concept of your multi-programming. How many processes are going to be executed? How are you going to utilize the CPU at the most? So this is the way you're going to utilize the CPU at the most. Okay. Scheduling of this kind, it's a very fundamental OS function. This is a very fundamental, very basic operating system concept. Almost all the computer resources are scheduled before the use. Sorry, what do you mean by all the resources? Don't think that resource means it should be an input device, output device, or a memory. Even the CPU is also a resource. CPU is one of the primary resource. So allotting or scheduling the resource is necessary before the use. Okay, scheduling is central. The operating system design. It's a very common point. Okay. So I hope you understand the multi-programming. So you need to think of two queues at least. There are many queues. The two queues are one in the memory is the ready queue and there is a IO queue. Okay, we still have waiting queue or before it comes to the ready queue, the process is in the waiting queue. So there are many queues, you need to remember it. Okay. Okay, now let's see the two concepts. What are the two concepts is CPU burst and IO burst. What do you mean by CPU burst and IO burst? Here the CPU burst means the uh, the process executing or the process is executed by the CPU. The time it takes and during the duration of the process in the CPU while its execution. That is CPU burst. Okay. If it is waiting for the input and output devices, that is called IO burst. If the process is in the CPU and the CPU is executing that process, that's called CPU burst. Okay then. So just see it here. The CPU scheduling depends on the property of the process. What does it mean, property of process? Maybe some process may have more input and output request. Some process may have more computations, less input output request. Okay, so that's the thing I'm telling, the property of process. So because what I'm trying to is, last chapter you studied CPU bound process, IO bound process. CPU bound process means the process is doing most computations. So CPU is busy all the time for the process. IO bound process is the computer is doing many IO devices, sorry, many IO requests, many IO tasks. That is called IO bound process. Meaning to say less CPU calculations. You get the idea? That's the thing here. Here it is. Yeah, can you see here from here? Yeah. See, CPU burst means, so it is like loading something, storing something, and etc. etc. Read from a file, whatever. Okay, so that's CPU. IO burst here is, see, it's waiting for the input output devices, and the process goes to the CPU burst means it store an increment index, write to a file, etc. etc. IO burst means it's waiting for IO. So the process, the job contains something to be done by the CPU and something to be done by the IO devices. It's mixed kind of task. Okay then. So the process normally it alternate between the two states. So what are the two states? CPU burst and then the IO burst. So first maybe CPU burst and then it goes to the waiting IO burst and then it comes back to the CPU burst or IO burst, something like that. Eventually, the final CPU burst, the last statement to be executed by the CPU is the terminate execution. The process terminates the execution. So how it terminates? System.exit will be executed. The exit call. This exit call will be executed. When CPU executes the exit system call, it terminates the process. So last final CPU burst is to terminate the process. Okay, so let's continue some more. Here in the CPU scheduler, so what is the task of the CPU scheduler? Whenever the CPU is idle, idle means CPU is not executing any process. So the OS should select one of the process from the from the ready queue. Here it is, from the ready queue for execution to assign it to the CPU. The selection process is carried by the short-term scheduler. This was the one I told you. Another name for short-term scheduler is CPU scheduler. Okay then. So what is the CPU scheduler is? You have the ready queue. So this is your ready queue. So when there is a process and the CPU is now idle, so this is your CPU. The process is executed into CPU and it's moved out maybe waiting queue or IO queue, whatever is it. Now the CPU is free. So the scheduler, it has many processes here, is it? So the scheduler select a process from the ready queue, assign it to the CPU. So who is doing this? CPU scheduler is doing this. So CPU scheduler or the short-term scheduler selects a process from the ready queue and assign it to the CPU. Okay, when the CPU is idle, the CPU is like not executing any task. Okay, so when the CPU is idle, the short-term scheduler selects one of the process from the ready queue and schedule to the CPU, assign it to the CPU. Okay. When this is going to happen, when one of this situation happens, so when one of this following situation happen, the CPU scheduler will select a job from the ready queue, assign it to the CPU. So what are the situation? Which situation? So any one of the four situation. What does it mean, any one of the four situation? When process running in the CPU is moved to the waiting state, or when a process running in the CPU is moved to the ready state, or when a process is in the waiting state and it is ready now. Process is in the waiting queue and it is ready now. Okay. That is moved to the ready state, from waiting state to the ready state. Or when a process terminates. So when any one of these situations happen, then the CPU scheduler will be called. Take a process from the ready queue, assign it to the CPU. Okay. Sometimes process will be executing a CPU will be executing a process. Process will be executed in the CPU. Sometimes this process will be moved to the waiting queue. So this is what you call waiting queue. Maybe it is waiting for the IO to finish. So this P1 is moved to the waiting queue sometimes. Sometimes, who knows, this process will be moved to the ready queue. Okay, sometimes this happens also. This process will be moved to the ready queue and there is an interrupt. Okay. Sometimes the process P1 finish execution, that is terminated. When a process is over, so the job is over, it's now terminated. Okay, finished its execution. So in these cases, you have the CPU idle, doing nothing. This situation is, sometimes you have a waiting queue, waiting for the IO devices to finish job like printing or reading a data or something like that. Let's assume that the job is over. The job is over. This process is moved to the ready queue. You will move the process to the ready queue. Okay. Okay then. So from waiting queue to the ready queue. Can you see here? The process switches from waiting queue to the ready queue. So when any one of these situation happens, then the CPU has to schedule a process. Sorry, the scheduler has to take a process, assign it to the CPU. Okay then, so this is the idea. Just hold on a minute. Okay, now let's move on to the scheduler, like kind of uh, explanation, like when the scheduler will be done and what are the choices, two types of scheduling, something like that. Let's see that. For situation 1 and 4, there's no choice in terms of scheduling. Okay, what do you mean by the situation 1 and 4? The previous slide, I mentioned 4 situations. When any of the 4 situation happens, in the CPU scheduler, it carries out the selection process. It selects a process from the ready queue and assign it to the CPU. Okay, the selection process is done when any of the situation happens. Okay, then remember we have ready queue. Ready queue is in the memory. That contains the processes, list of processes ready for execution. Ready for execution. That's the meaning that ready queue. Okay. Waiting queue is containing a list of process waiting for the IO. Waiting for the IO. That's called waiting queue. Queue. From the name you can have the understanding. Okay. In one more queue we have wait a minute. Um, just a second. Sorry, waiting queue is the list of process waiting to be moved to the ready queue. I'm sorry, the waiting queue is the list of process waiting to be moved to the ready queue. Okay, then the one waiting for the IO device is device queue. Okay, fine. Okay, then so you need to remember these things before we continue with that. Okay, now let's remember the situations from running queue to the waiting queue. Okay, from running queue to the waiting queue. Okay, then and then from running queue to the ready state. Sorry, it's not a queue, it's a state. Running to waiting, running to ready, and here waiting to ready, and then here it is terminates. Fine. So here remember these 4 situations, and then we will continue with the explanation. So running to the waiting queue. So mean to say that assume that CPU is executing a process. Okay, sometimes it moves the process out of the CPU and put it onto the waiting queue. This is one situation happens. Okay, and the second situation is when a process terminates. So remember the number 1, number 4. A running process is moved to the waiting queue. So the state of the process, it is changed from running state to the waiting state, or state of the process change from running to terminate. There are many state, I'm talking about the state. Okay, so in these 2 situations there is no other choice. For situation 1 and 4, there is no choice that the scheduler has to take a ready process and assign it to the CPU. It has to pick a new process from the ready queue and assign it to the CPU for execution. Schedule it for execution. But for situation 2 and 3, there got some choices. Okay, for other 2 situations, we still have choices. Okay, then. Okay, and another thing, for scheduling it place only under circumstances 1 and 4, we say that this scheme is called non-preemptive. There are 2 terms we will be using it. What is the 2 term is non-preemptive and preemptive. What do you mean by non-preemptive is another name is cooperative. So when you say non-preemptive, CPU is allocated to the process means the process keeps the CPU until it finishes. Okay, then mean to say that when you assign a process P1 to the CPU, P1 keeps the processor until it finished the execution. That is the meaning of non-preemptive. Okay, then here it is. Under non-preemptive, once the CPU is allotted to a process, the process keeps the CPU until it releases the CPU. Okay, so when it will release the CPU until it finish the process, or else it will be switching to the waiting state. So this is the one I was telling. When a process is moved to the waiting state, mean to say it's waiting for something. Okay, maybe it's waiting to be moved to the ready queue, it's waiting for the IO to complete the job. Okay, so it's waiting for something. Okay, the process from the waiting queue, it will be moved to the ready queue. From the ready queue, it's assigned to the CPU. You get the idea? So from the waiting queue to the ready queue, and from the ready queue to the CPU. Okay, then from waiting queue to the ready queue is done by the long-term scheduler, and from the ready queue to the CPU is by the short-term scheduler. Remember these two things. Okay. This non-preemptive, actually we are talking about the non-preemptive, is it? Non-preemptive means once the CPU is given to a process, it keeps it until it finishes its execution or until it moves to the waiting queue. Okay. This was the scheme or scheduling method. It's used in the old operating system like Windows 3, the old operating system. Even the old Mac operating system also had this preemptive. Okay, but the latest operating systems support, the old operating systems support non-preemptive. Okay, so the latest one these days, the operating system supports preemptive. Even the new Mac operating systems, Windows new operating system, after Windows 95 things, they are using the preemptive scheduling. Okay, so it's not the case that once a process is allotted, it is still in the CPU until it terminates or until waiting for IO or whatever is it. It's not the case. There are some preemptive means the process assigned to the CPU will be taken out in other situations also. Okay, remember the point. Non-preemptive means the process is kept in the CPU, assigned to a CPU, it will keep the CPU until it terminates or until it's moved to the waiting state or waiting queue. Okay, but no, preempt means it's not the case. It's not like that. It's not like until you terminate, until it finishes the execution or until it's moved to the waiting state. No, it's not like that. In between, it can be removed from the CPU and kept in the waiting queue. Like after 2 minutes, the process will be removed. This is what you call like round robin preemptive method or priority based. When a new process comes and that is a more important process, so the CPU will be that process will be taken out of CPU and the more important process will be assigned to the CPU. Can you get the idea? In preemptive, you don't keep the process for a long. At any time, it can be removed out of the CPU. Okay, that means when a new priority process comes in, high priority process comes in, you will take out the process from the CPU and assign a high priority process to the CPU, or else every 5 seconds or every 2 seconds to remove the process from the CPU, something like that. Okay, so that's preemptive. Okay, we will see in detail preemptive and non-preemptive. No worries. Okay, in upcoming slides we will discuss with examples. Okay. Um, Now we need to Okay, now let's see the dispatcher. So dispatcher, from the name you can able to understand the meaning of the dispatcher also. Dispatcher gives the control of CPU to the process. That's the main idea. Selected by the short-term scheduler. Okay, remember those things. We have the main queue here. These are the two main queues, and then here this is the CPU. So let's say this is CPU. And this is ready queue. Let me write R only, and this is the waiting queue. Let me write waiting queue. Remember, long-term scheduler takes the process which is in the waiting queue, move to the ready queue. When the process will be in the waiting queue, when the process is waiting for the input-output devices or whatever. Okay then. And who is doing the scheduling from here to here? Who is moving? Long-term scheduler. Okay, another name is job scheduler. We already studied this one in chapter 3. And from ready queue to CPU, who is going to schedule? That is the short-term scheduler, CPU scheduler. You have many processes waiting here. Process P1, P2, P3, P4, P5. So select one process assigned to CPU. We will do this short-term scheduler or CPU scheduler. Okay then. And in between, when the CPU scheduler assigns a process to the CPU, in between, we have a module called dispatcher, a component of the CPU scheduler called dispatcher. This dispatcher is a module, okay, and that gives control of the CPU to the process selected by the short-term scheduler. What are the function of the dispatcher? It switches the context. You know the context switch, we studied it in the last chapter. What do you mean by context switch? Every process has some states, is it? So context switch means saving the state of the old process in its process control block and loading the state of the new process in its process control block. That is called switching the context. Another name, context switch. Okay. Second one is switching the user mode. What do you mean by switching the user mode? The another process is switching to user mode. So in this case, when you switch to the user mode, you mean to say the process is it's like kind of going to be executed and then jumping to the proper location on the user program. So which task has to be executed. So you will be, going to the proper location, like proper statement of the user program, and restart the program, like continue for the execution. Proper location in the US program, start resume execution, because maybe half of the program was executed before and now we need to continue with the second half of the program, something like that. Okay, so the dispatcher has to be, the condition for the dispatcher is it has to be as fast as possible. This is one thing. And because because the process is already scheduled to the CPU, and after the dispatcher only the execution will be starting. Okay, but the CPU is now waiting for the dispatcher to finish the task. So the dispatcher has to be as fast as possible, and it is invoked for during every process switch. Whenever the process is moved, taken out from the CPU and a new process is assigned to CPU, whenever there is a change, then this dispatcher is called. Why? For the context switch. It saves the state of the old process in its PCB, process control block, and load the state of the new process in its PCB, process control block. Every process has a PCB. Okay then. So that's called process switch. The time it takes for this dispatcher to stop one process and to start another running process. This time it stops the execution of one process and starts the execution of the new process. So the time it takes to do this called latency. What do you mean? Dispatch latency. Delay. There should be a delay, by the way. Whenever you see latency, latency means delay only. So that will be very short. That has to be too short. That's what I was telling. Dispatcher has to be fast enough because it's a delay, by the way, latency. So that time is called dispatch latency. Okay, let's move on to some of the criteria for the CPU scheduling. As I mentioned in the starting of the lesson, we have many algorithms for CPU scheduling. Every algorithm has different properties. Okay, so based on something, we need to choose a particular algorithm. Okay, then. So let's see before going to the different algorithms, the varieties of algorithms. We need to see some criteria based on what we are going to choose the algorithm. Do we want to have shortest time, or do you want an efficient way of scheduling? So based on that, we need to select the particular suitable scheduling algorithm. So let's see the characteristics, which characteristics are going to be used for comparison, so that you see the differences between the algorithms and you can decide the best one. Okay, then first one is utilization, CPU utilization. So here, if you want to keep the CPU as busy as possible, you don't want the CPU to let sit idle. Okay, so make use of the CPU. So in this case, you want to utilize the CPU. Actually, when you say CPU utilization, in percentage, it will be 0 to 100 percentage. We can't say that the CPU is used 100 percentage, no, and CPU is used 0 percentage. No, we can't say that. Okay, but generally the range is from 40 to 90%. So 90% of the CPU time is utilized, something like that. Okay. The range, the CPU utilization range is normally in the range of 40 to 90%. Okay, it's the utilization, like keeping the CPU busy. That is what you call CPU utilization. The next criteria is throughput. When you say throughput, this means number of tasks or process executed per unit time. What do you mean by number of tasks executed? Like in 1 second, how many tasks are completed by the processor? That is throughput. Okay, let's say in 5 seconds, how many tasks are completed? If I say that 20 tasks are completed, yeah, very good. That throughput is high. That means CPU is doing execution fast, something like that. If I say in 5 seconds, CPU finished only one process, no, that's not a very good. Okay. Can you get the idea? The throughput has to be like improved throughput, like increased number. We need to have an increased number. So that's what we call improved throughput or efficient. Okay. But long process take more time. So when you execute long process, you can't have many number of processes completed in unit time. That's not possible. Okay, now it's the turnaround time. When you say turnaround time, that is the, you can say a delay or an interval from the time of submission of the process to the time of the completion of the process. When the process is submitted, Okay, what do you mean by process is submitted? You know the queues, just now I mentioned that you have waiting queue, this is what you call waiting queue, and then you have a ready queue, and then you have the CPU. This is CPU, it looks like a queue. Yeah. So when a process is ready, let's say there is a process ready for execution, it will be moved to the ready queue. Okay, so from the time the process comes here until the process is terminated, the time it takes, that is what you call turnaround time. Remember, during this time, process will be moved back to waiting queue. When there is a input output process, and then it will be moved again to the ready queue. Sometimes it will move to submitted to CPU and move back to waiting queue, whatever. Okay, but the idea here is when a process is moved to the ready queue for the first time. Okay, move to the ready queue until it finish its execution. In between, it will be moved back to the waiting queue and come back to the ready queue and assign it to the CPU. There will be many things going on, but no worries. From the start of the time, when it comes to the ready queue for execution, until it finish execution, how long it takes, that time is called turnaround time. Remember, here is the point. Here it says that sum of periods spent waiting to get into the memory, waiting in the ready queue, executing in the CPU, and performing servo, whatever. All these time are included. Okay. Now, waiting time. So here this waiting time is the amount of time the process has been waiting in the ready queue, because I told you there are many queues you have here. Here this is the waiting queue, and you have the ready queue, and you have the processor. Is it? When the process is ready, it's moved from the waiting queue to the ready queue. And all the processors will be waiting, and CPU scheduler will select one process and assign it to the CPU. So how long it takes for the CPU scheduler to select a process? So it will be waiting in this ready queue for some period of time. That amount of time is called waiting time. Now let's move on to the response time. Response time is something like the process may be asked to do some task, like maybe to display something or to take input from something, or to print something, whatever is it. So when the time it starts the execution until it starts to respond, the first response, no matter that the complete execution, finish of the execution, no matter the finish of the execution, but first it starts to respond. Okay, that time from the start of the execution until the time it starts to respond. Okay, in this point you have to remember the first response, until the first response. Okay, so that time is called a response time. No matter that completion of the execution, I don't care about the completion of the execution, the first response it produces from until that time. Okay, this is the more important here. To maximize the CPU utilization and throughput, and to minimize the turnaround time, waiting time, and response time, mean to say that you need to choose an algorithm so that it can maximize the CPU utilization. So remember, you need to maximize, increase the CPU utilization, increase the throughput. Throughput means number of tasks executed per unit time. So these two has to be increased, but what has to be decreased? Turnaround time, waiting time, and the response time. This has to be decreased. So what to maximize, you have to remember. Okay, there are many things. 5 terminologies or 5 criterias we saw. 2 of them has to be increased, 3 of them has to be decreased. Okay, so that's the thing it's mentioned here. We need to maximize something and we need to minimize something. Okay, so this is mentioned here. So remember that point. We have certain algorithms. Here, what are the algorithms we have is first come, first served scheduling algorithm. And then we have like priority scheduling algorithm, round robin. There are many algorithms we have here. Okay, so okay, let me go through first. From the diagram, I will explain and then we will see in depth. Here it is. Yeah. This is the first come first serve scheduling algorithms. No worries. These 4 algorithms I will make a video with the exercises and then you can see it from the blackboard. Okay. Now I'm going to give an overview of the algorithm only. Assume that you have certain process like here it is. Let's assume that you have the process P1, P2, P3, 3 processes. And the 24 P3 means the burst time. What do you mean by burst time? How long it takes? CPU burst time. How long it takes to complete the execution. That's the burst time. See, first process P1 takes 24 unit of time. P2 is going to take 3 unit of time and P3 going to take 3 unit of time. So in assume that all these process arrives in the same time. Okay, at the same time all the process are coming. Then assume that you go in first out manner. Like which one comes first? Which one comes? Like you are all coming to the class at 10 o'clock means enter the room first. You all come in 10 o'clock, but in minute there will be a difference. Can you see that? In seconds there will be a difference. So let's assume P1 comes first. The CPU is assigned to P1. 24 unit of time it is taking. Then P2 is assigned. Then P3 is assigned. Okay, so can you see here the waiting time? P1 doesn't wait. The time it comes, it's assigned to the CPU. P2 waits 24 units of time. P3 waits 27 unit of time. This is the waiting time. P1, P2, P3. Average waiting time, you add all these waiting times and divide by 3. Number of process is 3. Okay, then you get the idea. So this is your average waiting time, 17 unit. Why 17 units? 17 is a big number because of the reason the first process you assign to the CPU is the long process. It takes 24 unit of time. Okay, assume one other situation. Because this algorithm is first come first serve scheduling algorithm. Meaning to say, which job come first, you assign it to CPU. Which job come next, assign next. Okay, something like that. Assume that in case the same situation, the arriving is in this order. So the process arrived in this order. P2 first, P3 second, P1 later. Third process. Okay, so P2 is assigned. Can you see here? It doesn't wait. The waiting time of P2 0. It doesn't wait. The time it comes inside the CPU, it's assigned. Sorry, the time it comes inside the ready queue, it's assigned to the CPU. P2 assigned. Then P3. The next P3. It waits for 3 unit of time. P1 wait for 6 unit of time. So this is the waiting time for P1, P2, P3. So the average waiting time, you sum up all and divide by 3, you get 3. See, very less average waiting time. Same scenario, same 3 process, same burst time. Now we get a small average waiting time because the order. In case if a short process is served first and the long process is served later, the average unique time is going to be lesser. Okay then. It's not in our hand. Which process comes first, no one knows. Okay. Anyway, this is a scenario only. This is one algorithm. First come, first serve. So which job comes first? The ready queue, that job will be scheduled to the CPU. And the next one is shortest job first, SJF. That means shortest job first. This is very simple. Can you see here, this scenario, we have 4 processes, P1, P2, P3, P4. There are 4 processes. These are the burst time. Burst time means the CPU time, how long it takes for execution, to finish the execution. So that's fine, no problem. These are the arriving time. In the previous scenario, I told you they are all came in the same time. It differs only in a minute or a second. Now we have a different arriving time. One come in 0th second, another one come in the second 2, and then another one comes in the 4th second, and another one come in the 5th second. So let's assume these are all in seconds. Okay. There is a difference in the arriving time. No matter, it's not a problem. Whichever comes first comes next. We are not going to bother about that. The idea here is shortest job first. Actually, what you say that we need to have the smallest next CPU burst, which is going to have the smallest next CPU burst. That one will be assigned. That process will be assigned. This is the key term. Shortest or smallest next CPU burst. Let's assume this example. Of course, at time 0, there's only one process is there. No other process. So, of course, by day, by the way, remember this or all. By the way, this is not the correct slide. If I uploaded already, this is all 0.0, same time. They don't come in the different time. So this is also 0, this is also 0. Okay. Remember, there is a mistake in the arrival time. So these are all come in the same time, by the way. Okay, remember this one. If I will upload it with the correct slide later, but if you have it, note down. So here in this exercise, they are all came in the same time. So they are all came in the 0th time, and the burst time is 6, 8, 7, and 3. So which is having the shortest burst time? P4. So P4 is assigned now. Okay. After which one is having the short time, this one, P1, because 6 is small, then 7 and 8. So P1 is assigned. So it takes how many, like kind of 6. So already 3 units are done, plus 6, so it's now 9 units. And after that, which one is smaller? P3 is smaller. So P3 is assigned, the unit burst time is 7. So 9 plus 7 is 16. Can you see here? And the leftover job is 8. So, sorry, leftover job is P2 with 8 unit. So 16 plus 8, 24. So here the average waiting time, P4 doesn't wait, it's 0. P1 waits for 3 unit of time, P3 waits for 9 unit of time, P2 waits for 16 unit of time. So the average waiting time, sum all the waiting time divided by 4. So you will get the average waiting time. No matter, I'll make the more exercises and you will see it in the blackboard. So this is the shortest job first. The other one is priority scheduling. What do you mean by priority is? No, this is the shortest. I think you can able to see the priority scheduling. So based on the priority of the process, the high priority process will be assigned to the CPU. That's the idea. Priority. Every process will be given a number. That number will tells you the priority. Okay, high priority, low priority. From the number you can understand which process is having high priority and low priority. So the high priority process will be assigned to the CPU. Okay, so that's the is called priority scheduling algorithm. Okay then, actually it's in the range of 0 to 7 or 0 to like 4,000 or something. But never mind, low number means high priority. Like example, a process is having a priority 1. 1 is a small number. Small number means high priority. If a process has 10, 10 is a big number, so less priority. Okay, so you will be choosing the high priority process. Let's see one example. Yeah, this is one example. Here you have 5 processors. They are all waiting in the ready queue. And these are the burst time. Burst time means the time it needs for execution. It needs 10 unit of time. It needs 1 unit of time, 2 unit of time. That is what you call burst time. And this is the priority. By the way, it's not aligned properly. It has to go here. Okay, it's the priority. I told you here in this exercise, low number means high priority. High number means less priority. Okay, just assume this way because some textbook use the other way around. Okay, that's what I am telling again and again. Okay, let's assume how this priority scheduling works. This is the burst time, this is the priority. So which is having high priority? P2. Can you see here? Because it has a low number, 1. So P2 is given. How many time it needs? 1 unit of time. Okay, 1 unit time. And the next priority is P5 because number 2. So P5 is assigned to the CPU. The unit of time is 5. So 1 plus 5, 6. 5 unit of time it needs for execution. Then who is having the low priority? P1 because the priority is 3. Okay. The burst time is 10. So 6 plus 10, 16. Here comes the 3 because priority is 4 and the execution is 2. 16 plus 2, 18. And the last one is, of course, 4 with high priority 5, unit of time 1. So at time 18 it starts, at time 19 it finishes. 1 unit of time. The average waiting time you can take it from P2 doesn't wait. P5 wait for 1 second. P1 wait for 6 unit of time. P3 wait for 16 unit of time and P4 wait for 18 unit of time. So when you add up all those things and divide by 5, you get something. Oh, by the way, these are all in milliseconds. Okay, this best time, they are all in milliseconds. Okay, this is about priority scheduling. And the next is round robin. Before going to round robin, we need to see the preemptive and non-preemptive. I mentioned in the beginning of the class, these days the operating systems are preemptive, using the preemptive scheduling. Those days the old operating system uses non-preemptive. What does it mean, preemptive, non-preemptive is when a process, can you see here? So the priority scheduling can be either preemptive or non-preemptive. Okay, fine. So preemptive priority scheduling will preempt the CPU if a high priority or if the priority of the newly arrived process is higher than the currently running process. That's what you call preemptive. Non-preemptive means once the process is assigned to the CPU means it will keep the CPU until it finishes or until it moves to the waiting state. Non-preempt means the process will keep the CPU. Okay, it will keep the CPU until it finishes the execution or until it moves to the waiting state. Okay, it is like waiting for the IO or something. Okay, but preemptive means it's not like that. When a high priority process comes in, the currently executing process will be kicked out of CPU. Can you get the idea? Or when a time elapsed, I mean to say when 2 milliseconds elapsed, the new process will be moved in the CPU. You get the idea? That's preemptive. These days, operating systems are using the preemptive scheduling. Okay, that's effective, by the way. So that's the idea, preemptive or non-preemptive scheduling. Okay, and you will see one exercises, I mean, an exercises for preemptive and non-preemptive in the blackboard after the class. Okay, and next we move on to round robin. Okay, just a second. Okay, let's see the round robin. I hope you can able to see it. Okay, in round robin, the idea is from the name you can able to see that it goes in a circle, it goes in a round. So every kind of time quantum, or you can call it as a time slice, you will have a small unit of time, and the process will be assigned to the CPU for that time frame. Okay, you call it time slice or time quantum or whatever is it. For example, in case the time quantum is 100 milliseconds. Okay, let's say the quantum is 100 millisecond. So the process one, for example, will be assigned to the CPU for 100 millisecond. Even though the process finish execution, not finish execution, P1 will be moved out of the CPU, and the new second next process will be assigned for 100 quantum. Okay, this is the idea. So every 100 quantum, the process will be moved out and a new process will be assigned to the CPU. The process will be moved out means it will be moved to the ready queue, and a new process from the ready queue will be assigned to the CPU. So that's the idea of round robin. Okay, so this is especially for time sharing kind of system. Okay, it's mentioned here. This type of algorithm is designed for the time sharing system. Okay, it's similar like first served scheduling algorithm. It's like one is assigned and the other one is assigned, other one is assigned, something like that. First in, first come only. But first come, first served, there is no preemption. Here we have the preemption. Preemption means uh, what is preemption is when a process is assigned to CPU, during its execution will be taken out of the CPU. Okay, no matter it's finished execution, not finished execution, so it will be taken out. That is what you call preemption. Okay, that preemption is added with the FCFS. That's your round robin. Okay. You need to know what is a time slice, I mean to say a time quantum. It's a small unit of time, unit of time frame. Okay, that's the idea. It ranges from 10 milliseconds to 100 milliseconds. So the CPU scheduler goes around the ready queue, allocating the CPU to each process in that time interval. So every 100 millisecond, it will go around the CPU, ready queue, and take the process, assign it to CPU. Take the next process, assign it to CPU. Okay. So this ready queue is treated as a first in, first out queue of the process. New process will be added to the tail of the queue, and the scheduler picks the first process in the ready queue and it sets a timer. So the timer will be decremented. It will be 100, then 99, 98. When it reaches the 1, mean to say the 100 time is over. So the dispatcher, it takes another process and assign it to the CPU. Okay, and it switches the process. It removes the process from CPU, assign the new process to the CPU. Okay, fine. So that's the round robin. So these are all the different types of scheduling algorithm. There is one more. Yeah, another type of scheduling algorithm. It's multi-level queue. It has been created for situations in which the process are easily classified into different groups, because we can't say processes are of same. We have different groups of processes. For example, division is made between the foreground process or the background process. Foreground process means interactive process, user process. Background process means the batch process. So these two types of process have different response time. They are not the same. And they have different scheduling needs, because the foreground process may have priority over the background process. So in that case, we will be having multi-level queue scheduling algorithm. It partitions the ready queue into several different queues. So one ready queue will be divided into more separate queues. The process are permanently assigned to one queues. Okay, because already I mentioned that there are two types of process, foreground and background. Interactive process or the batch process. Can you get the idea? So each queue has its own scheduling algorithm. So interactive process queue has its own algorithm, and the batch process queue has its own algorithm, not necessary to be the same scheduling algorithm. Separate queue may be used for the foreground or background process. Can you get the idea? Depends on the type of process, they will be having the different algorithms. Okay, you will have the ready queue is divided into, broken into many different queues. Each queue has a kind of a process, a type of process. If you have 4 different queues, each queue will have its own type of process. Okay, that's the idea, because not all the processes are same. Every process may have its own requirement, its own priority. Okay, so based on that, ready queue is divided into different queues, and different queue will have different scheduling algorithm. So this is one example, like a system process or in this queue, the top one. Okay, this is system process, interactive process, or editing process, batch process, and then the student process. The one on the top is having high priority, and one on the bottom is having low priority. So each queue is having its own priority. Okay, no process in the batch queue, for example, could run unless the queue for the system process or interactive process or whatever are empty. So if a process in this batch queue needs to be executed, first of all the process in the system queue, interactive queue, editing process has to be completed. If there is a process, it exists in this queue, a process in the batch queue can't be executed. That's the idea. Can you get the idea? So this is about multi-level queue. So that's all about the scheduling algorithm. So what's the pending is exercises for the 4 type. There is no exercise for the multi-level queue, by the way. I've got exercises for the previous 4 queues, which is the first come first serve, shortest job first, then the priority, and the round robin. These are the 4 scheduling algorithms, and there is some exercises for the algorithms. What do you mean by exercises is, I'll give you the list of processes, their respective burst time, and the arrival time, and the priority. In case if it is a priority scheduling algorithm, I'll give you the priority. In case if it is a round robin, I'll give you the time slice, the time quantum. All these details will be given, and you may have to draw the sequence, execution sequence, which is executed first, which is executed second, and what is the average waiting time. Okay, turnaround time. I did not mention the turnaround time in the slide. In the exercises, I will mention the turnaround time also. Okay, so that's about the chapter 6. We finished with the chapter 6. Only the pending is exercise. I will upload it in the Blackboard by today in a while. Okay. Anybody has any questions? Of course, you need to have the exercises to be worked out. Then you will have a clear understanding. After the exercise, try to solve by yourself. After you try to solve, then only you will have problems and doubts and everything. Can you get the idea? After I upload the exercises in the Blackboard, you try by yourself. I will have the explanation in the exercises, but you try to solve by yourself without seeing my explanation, and then you can have the doubts. Then only you will come across your problems. Okay. So, any questions, any doubts? Okay, Sahar doesn't have anything. How about others? I couldn't able to see it. Someone said something. Okay, Noora and Mushara and Lusan and fine, no problem. That's good. How about Kola? Kola and Vejdan, are you fine with the chapter 6? That's good. That's good. Okay. Okay, by the way, this class I continuously continued until the end of the chapter. For next classes, what we will do, we will try to have some in between exercises. Okay, so that it won't be boring for you. So in between, we will have a short exercise for your understanding, and then we will try to continue something like that. Okay. If there is no questions, then we can leave the meeting. Before leaving the meeting, majority of you said, okay, no problem with the today's last lesson. But anyway, go through the slide. Just a reminder, first day we have the practical class. I will be starting the Ubuntu command line instructions. So you have to install the Oracle VirtualBox and the Ubuntu. So just a reminder, sorry, just a reminder, first thing is install Ubuntu with the VMware. Sorry, it's not Ubuntu with the VMware, not VMware. I'm so sorry. VMware with the Ubuntu first thing. Okay, and the second thing is the lockdown browser, because I want to give a small test, a practice test, not for marks. How can you able to use it? It's a kind of practice. So this is second requirement for the next class, Thursday's class, and the third. The third one is the reminder of the quiz 2. Week 5, Monday, we have our classes during our class time only, chapter 1 and 3. So this is about the third one. So three things I'm just reminding you. So please keep it in mind for next class. Do not forget the Oracle VirtualBox with the Ubuntu, please. If you couldn't able to do lockdown browser, at least we have time. Maybe then later on we can do, but this one is more important. I have to start this week practical part. Okay. The first class we will go with this virtual meeting, and later on we can do it maybe like kind of using the video lessons at least. But the first class we need to do at least virtual meeting. Okay. So is it fine? If no questions, then we can leave the meeting if there is no question. Just a second. Yes. Okay. Majority you said yes. Okay then. So I will make an announcement for the quiz one so that you will have it in the email, so you won't have any problems in the conflict. If other teachers say something, you can still remember it. Okay, I will make an announcement for the quiz one. Okay, week 5, Monday class, and chapter 1 and 3. Okay, so if there is no questions, no doubts, then we can end the meeting now. And if you have any questions, no worries, you know my email. You can send me the problems or inquiries. Meanwhile, please try to install the VMware and Ubuntu. Okay. Even during installation, if you still have any issues, you can screenshot that one and send it to my email. Okay, so that I can able to see what's the problem. Is it fine? Okay, then thank you for attending and see you on Thursday's class. Okay, bye.